Properties of ionic compounds. In our last episode, we learned that a convenient method proposed by G. N. Lewis involves putting dots to represent the valence shell or the outermost shell electrons around the symbol of an element. Such representation is called electron dot structures. We also learned that sodium atom is represented by Lewis dot formula as Na dot, which means that one electron remains in the outermost shell. Chlorine atom is represented by Lewis formula as chlorine with 7 dots. 7 dots means 7 electrons in the outermost shell. Formation of an ionic bond can be depicted as shown on screen. Let us now try to represent fluorine and oxygen atoms by Lewis formulae. Fluorine has 7 electrons in its outermost shell, so it is shown with 7 dots around its symbol. Thus, we represent fluorine atom as shown on screen. Similarly, oxygen having 6 electrons in its outermost shell is represented as 6 dots around the symbol of oxygen. We represent an oxygen atom as shown on screen. Let us now learn about representation of magnesium 2+ ions according to Lewis formulae. Magnesium atom has 2 outermost electrons, but in forming the magnesium ion Mg2 positive, it loses both these electrons. Mg2 positive is represented as Mg2 positive without any dot. This means that there are no outermost valence electrons in the outermost shell. Let us now learn about representation of oxide ion O2 negative. An oxygen atom has 6 valence electrons. It can acquire 2 more to achieve the noble gas configuration, that is 8 electrons, to form an oxide ion. The Lewis formulae of oxide ion is as shown on screen. 8 dots represent 8 valence electrons. Fluoride ion also has 8 electrons in its outermost shell, so it is also represented as shown with 8 dots. Sulfide ion, that is S2 negative ion, also has 8 electrons in its outermost shell, so it is also represented in the same way as fluoride ion. Let us have some illustrations to understand it better. Magnesium, like all other alkaline earth metals, has 2 electrons in the outermost shell. Thus, to achieve a noble gas configuration, that is 8 electrons in the outermost shell, it must lose 2 electrons to form a bipositive ion, Mg2 positive ions. It can be represented according to Lewis's dot formula as shown on screen. Magnesium atom is having 2 electrons. Its atomic number is 12. Electronic configuration of K shell is 2, L shell is 8, M shell is 2. Mg gives Mg2 positive ions and 2 electrons. No dot in a shell means that M shell is empty. K shell has 2 electrons. L shell has 8 electrons and there is no electron in M shell. Chlorine, a non-metal, has 7 valence electrons in its outermost shell. To achieve the noble gas configuration, it has to get 1 extra electron. But the number of electrons lost in forming an Mg2 positive ion is 2. Number of electrons lost by magnesium is equal to number of electrons gained by the chlorine atoms. This is possible only when there are 2 chlorine atoms, each taking up 1 electron to achieve the noble gas configuration. One chlorine atom accepts 1 electron to form chloride ion. Another chlorine atom accepts 1 electron to form another chloride ion. To sum it up, 2 chlorine atoms accept 2 electrons to form 2 chloride ions. Electronic configuration of all the 3 ions: 1. Magnesium 2 positive ions and 2 chloride ions have 8 electrons in their outermost shells. This can be represented by Lewis formula as shown in the animation on screen. 1 Mg2 positive ion will bind itself to 2 chloride ions to form an electrically neutral ionic compound. In magnesium chloride, there is no net charge. All the charges are balanced. The forces of attraction between Mg2 positive ions and the 2 chloride ions are electrostatic in nature, which results in the formation of an ionic or electrovalent bonds. Let us perform an activity for preparation of magnesium oxide. For this, we take a magnesium metal wire and keep it on top of the flame of a burner till it catches fire. What do we find? We find that the magnesium wire burns with a sparkle and forms a white solid magnesium oxide, which consists of magnesium 2 positive ions and oxygen 2 negative ions respectively. We will now learn about formation of magnesium oxide. This can be explained as shown in animation. Magnesium atom releases 2 electrons to become magnesium 2 positive ion. Atomic number of magnesium is 12. Electronic configuration is 282. Lewis represented the process as is shown on screen. Magnesium loses 2 electrons to form magnesium 2 positive ions. Here, the 2 dots represent the outermost electrons. The oxygen atom belongs to a group 16 of the periodic table. It has 6 valence electrons. It can require 2 extra electrons to achieve the noble gas configuration and form O2 negative ions. Oxygen accepts 2 electrons to become oxide ion, that is O2 negative ion. Oxygen has electronic configuration of 2,6. Oxide ion has electronic configuration of 2,8. The oxide ion now has 8 electrons in outermost shell, which is represented by 8 dots. Transfer of electrons from magnesium atom to oxygen atom. The 2 electrons lost by the neutral magnesium atom in forming one magnesium ion have been taken up by one neutral oxygen atom to form an oxide ion. The resulting oppositely charged ions of magnesium and oxide are held by the strong electrostatic forces of attraction. This forms an ionic or electrovalent bond between them in the ratio of 1:1, resulting in the chemical formula MgO for magnesium oxide. Formation of sodium oxide, that is Na2O. In the formation of sodium oxide, one oxygen atom requires 2 electrons to form O2 negative ions, that is oxide ions, and achieve the noble gas configuration. As one sodium atom can release only 1 electron, you require 2 sodium atoms to lose 2 electrons. This will form 2 sodium ions for 1 oxide ion. Let us take one example. Explain the formation of the compound between aluminium and oxygen, and according to the Lewis formula, derive the chemical formula of the resulting compound. Aluminium has 3 outermost valence electrons. It can lose all the 3 outermost electrons to achieve the noble gas configuration. Oxygen has 6 electrons in its outermost shell. It requires only 2 electrons to achieve the noble gas configuration. In order to form a neutral ionic compound between aluminium 3 positive ions and oxide 2 negative ions, we require 2 aluminium atoms to supply 6 electrons, forming 2 aluminium 3 positive ions, and our 3 oxygen atoms to gain 6 electrons, forming 3 oxide ions. The resulting chemical formula will be Al2O3. Let us now discuss the physical nature of ionic compounds. Ionic compounds are generally hard solids. This is because the ionic compounds are made up of oppositely charged ions arranged in a regular way in a lattice. The force of attraction between the ions is electrostatic in nature and is non-directional, extending equally in all directions. Ionic compounds are brittle in nature. Brittleness is the ease with which an object can be broken. This property is exactly opposite of malleability, that is, tendency to change shape without breaking, which is characteristics of metals. The reason for brittleness of ionic compounds can be related to the close packing of oppositely charged ions. On hammering or subjecting them to pressure, the arrangement of cations and anions gets distributed, resulting in an increase in the repulsive forces because of similarly charged ions coming closer. This results in breaking of the ionic crystals into smaller pieces. Melting and boiling points. Ionic compounds generally have very high melting and boiling points. Have a look at the melting point and boiling point to gain a better understanding about ionic compounds. Ionic compound sodium chloride has a melting point of 1074 Kelvin, boiling point of 1686 Kelvin. Lithium chloride has a melting point of 887 and boiling point 1600 Kelvin. Calcium chloride has a melting point of 1045 Kelvin and boiling point which is 1900 Kelvin. Calcium oxide has a melting point of 2850 Kelvin, boiling point which is 3120 Kelvin. Magnesium chloride has a melting point of 981 Kelvin and boiling point of 1685 Kelvin. As we know, the oppositely charged ions in the ionic compounds are held together by strong electrostatic forces of attraction. It requires a considerable amount of heat energy to separate the ions and melt or vaporize the compound. Let us see how melting point of sodium chloride is determined. Powdered sodium chloride is collected in a watch glass. The open end of the capillary tube is carefully pushed into the sodium chloride on the watch glass. The process is repeated until the tube is filled with solid powder to a depth of half centimeter. Now the sealed end of the capillary tube is gently tapped on a flat surface. The capillary tube should be filled up to 2 to 3 mm. It is stuck to the thermometer. The lower end of the capillary tube and thermometer are at same level. Observe the capillary carefully and note the temperature at which the solid starts melting. Note the temperature when the solid completely melts. Heat energy melts the sodium chloride. Melting is the process of converting a solid into liquid, whereas boiling is the process of converting a liquid into gas. Let us now learn about solubility of ionic compounds. Ionic compounds dissolve in polar solvents. Polar solvents like water have the capacity to dissolve many ionic compounds like sodium chloride. Most chlorides and nitrates of the alkali metals and alkaline earth metals are soluble in water. Not all the ionic compounds are soluble in water. For example, calcium carbonate is ionic but insoluble in water. Barium sulfate again is ionic but insoluble in water. Generally, ionic compounds dissolve in polar solvents like water. They are insoluble in all non-polar organic solvents like kerosene and petrol. We will now learn about speed of reaction. Ionic compounds react very fast. It is because the reacting entities are ions and they are already in this form in the solution. They only need to collide with the other type of ions to complete the reaction. A solution of table salt in water already contains sodium ions and chloride ions. If we drop a drop of silver nitrate solution which contains silver ions and nitrate ions, the reaction takes place instantaneously. And silver ion combines with the chloride ion to form silver chloride, which is obtained as a white precipitate. We will now learn about electrical conductivity of ionic compounds. Ionic compounds do not conduct electricity in the solid state because in solid state the oppositely charged ions have fixed positions. The ions are not able to move. However, when they are melted or dissolved in water, the crystal structure breaks down and the ions are free to move. These free ions conduct electricity. Sodium chloride ion compound behaves in the same way. The free ions in the molten or dissolved state can conduct electricity by moving towards oppositely charged electrodes. You can observe the movement of ions from the animation shown on screen. Sodium ions move towards the cathode, whereas chloride ions moves towards the anode.